Welcome to this video on linear independence. Linear independence is a kind of simple topic that is often hard to understand in terms of its formal definition. I think that people have a pretty good intuition as to what linear independence is when they see examples of it, and then when they look at the definition more formally, they lose sight as to what is going on. So let's talk about the intuition first, and then see if we can map that intuition into the definition. So if you're given a set of vectors and you're analyzing them, maybe for fun, and you're trying to work out if they're linearly independent or dependent, what you're asking is, out of all the vectors that I have in front of me, can I get rid of one and then still have roughly the same information? So can I sum vectors together to create new vectors and then have one vector that I don't actually need in summing them together? Is this vector just another representation of the other vectors that I have already? And if one vector can be represented by the vectors you already have, you can get rid of it. You don't need it, because that vector can be generated by just adding some scalar multiple of the vectors that you have already. And this idea of independence is when you eliminate vectors one by one that are dependent. Eventually, you're going to get down to a set of vectors that are completely independent. And if you were to eliminate any of those vectors, then you wouldn't have access to directions and vectors in terms of adding scalar multiples of vectors together that you did before. So let's look at some examples first. If we had the vectors 1, 1 and 10, 10, then this is a linearly dependent combination, because 10, 10 is just 10 times the vector 1, 1. So you can reach this direction as long as you're allowed to scalar multiply the vector 1, 1. In this case, 10 times 1, 1 is equal to 10, 10. So there's no extra information contained in this vector, and it is accessible by just multiplying this one by 10. On the flip side, 2, 3 and 2, 8 is linearly independent because you cannot reach the direction 2, 8 from 2, 3. The 2's are already constant across the vectors, and multiplying this to reach 8 here is going to take the first one away from 2. So this is a different direction to this one, and there's extra information added by having this vector, and together you can actually generate different directions by summing these together, unlike above. Okay, the third one, 3, 4, 4, 5, this is also linearly independent. This is more of a trick question for this one because the difference between them is 1. So it might look like they're dependent, but the actual direction that is categorized by 3, 4 is very different to 4, 5. If you don't find that easy to see, think about the direction 1, 2 that has a difference of 1 between them versus a million, a million and 1. A million, a million, 1 is almost just 1, 1 in the direction. And so, yeah, these are different directions. 5, 7, 10, 4, also linearly dependent because 2 multiplied by 5, 7 is equal to 10, 14. And then here, our first set of 3, this is going to be linearly dependent because we don't need the third vector 2, 3 to have extra information. We can just create that vector from 1, 0 and 0, 1. So 2 times 1, 0 plus 3 times 0, 1 is equal to 2, 3. So this is dependent, and we can get rid of this one here. And if you think about our coordinate system, the coordinate system is actually defined from adding two different directions together. The x-axis is actually the axis with direction 1, 0, and then the y-axis is just the direction 0, 1. And when we put down the coordinate, say 4, 2, we're actually adding 4 multiplied by 1, 0 plus 2 multiplied by 0, 1. And the stack of these vectors together gives us our coordinate 4, 2, or our vector 4, 2. And if you have linearly independent vectors as your axes, you just need any two linearly independent vectors, and you can generate the whole of r squared by the combinations of those vectors together. On the flip side, if you had linearly dependent vectors, like 1, 1 and 10, 10, you wouldn't be able to span all of R2 because you can't access a bunch of vectors that aren't in that direction. So written down here, R2 is spanned by these vectors added together with some constant in front of them. You can generate any vector you want, 11, 3, and then you can have 11 for C1, 3 for C2, and that will give us that vector. But on the flip side, dependent vectors like this one, 1, 1, and 2, 2, you cannot span R2 with these vectors. Okay, so this is just some intuition and some examples as to what linear independence and dependence is. And if we look at our formal definition here, vectors are dependent if you can represent one of them as just the scalar multiple sum of the other ones. So here it's written something equal to 0. But what that really means is you could take across one of the vectors to the right hand side and then divide everything by minus ck, and you'll have vk is equal to the sum of these vectors together. And they're independent if you can't do that. So there's no way to get 0 on the right hand side except by multiplying every vector by 0 on the left hand side. And this is a clean way of saying that the vectors can never be represented by the scalar multiple sum of each other, and they're independent if the only way you can get 0 on the right hand side is by just multiplying every vector by 0. So that's the formal definition that is made to talk about this concept here that we mentioned intuitively on this page. Okay, so to show that vectors are dependent, you just need to provide an example vector C that gives you this. So here when I said 10, 1, 1 is equal to 10, 10, then I could move that to the left hand side and I've got 10, 1, 1 minus 10, 10 is equal to 0. And so the C vector that I would use is 10, minus 1. And if you can provide the example of how they are actually equal to each other, you can show your linear dependence. Of course, you can't give the vector of zeros as your answer. That doesn't count. That's the trivial solution. To show that it's linearly independent, you need to show that there's no way that you can multiply the vectors together to give you 0, and that is showing that this system here is independent. So if we take some examples and look at it, 1, 2, and 10, 20 are linearly dependent because this is equal to 0, 0, and the coefficients are not the trivial solution. 1, 1, and 1 minus 1 are linearly independent because if we look at a system here and try to solve it, we get an inconsistent system where after you do some work on your augmented matrix, you have minus 2 beta is equal to 0, which implies beta is 0. And then plugging that back in above, you get alpha equal to 0. So the only solution to this is just that they're zeros, and if you've demonstrated that here, you've shown that they're linearly independent. Okay. There's actually more ways that you can show this independent as well, and that is a deep connection in terms of linear independence of vectors and inverses and invertibility. So I'll just finish with a comment about that. A matrix A is invertible if and only if the columns of A are linearly independent. And by extension, A is invertible if and only if the rows of A are linearly independent. So A is invertible if and only if A transpose is invertible. The columns of A transpose are linearly independent, which means the rows of A are linearly independent. So we actually can apply a lot of these theorems together to make a chain of theorems that are biconditional, which means that if you prove any one of those conditions, it implies the rest of them are true. So this chain is the one that's given below. A is invertible, therefore there exists some inverse A such that A multiplied by A inverse is equal to A inverse multiplied by A, which equals to the identity matrix. That means that the transpose matrix is also invertible. That means the columns of A are linearly independent. The rows of A linearly independent. A times X equal to B has a unique solution for every system. The null space of A is equal to 0, and the determinant of A is not equal to 0. Sorry, the null space of A is equal to the set 0, the 0 vector. And any one of these things, if you can show it's true, implies the rest of them are true. That means that another way to show that you have linearly independent or dependent vectors is actually by using this bottom one here, working out the determinant of A, which categorizes your vectors in terms of the matrix. So the rows are equal to the vectors, and then you take the determinant. And if the determinant is 0, it means that they're linearly dependent. And if they're not 0, it means that they're independent. Yeah, so if you prove one is true, you prove that all are true. All right, thanks for watching this video, and I hope you found it helpful.